So welcome everybody to the ACOM seminar. Sasha is supposed to be up here introducing Louis, but Sasha is, as I understand, right now having a baby, so she's got the day off. She's on PTO today for a while. So we've known Louis for a long time. So Louis came to work here in our group. It was about 5 years ago now or something, for 6 months or something, and that was kind of an introduction of us to Louis also to UTLS activities, and he liked what he was doing, and then he ended up deciding to go to Fort Collins and pursue a PhD at Fort Collins. So he's been up there in the intervening time. He's been working with Thomas Berger, and Louis is very resourceful, because in the meantime, Thomas decided to go to Munich and pursue a different career or different job in Munich, but Louis has stayed here and has been working on his PhD. He's written a number of papers on tropical cyclones. Today we're going to hear about what's cooling the tropopause. So, welcome.
Thank you, Bill. Before I forget to mention, please jump in, because I don't want to be talking at you guys for whatever amount of time. I'd rather have an exchange. And also, I have an excruciatingly painful headache right now, so I'll hang in there, but bear with me.
We do that to our seminars.
Yeah. That's great. I think it's courtesy of staring at my computer for way too long. So I guess the first thing I should say is that as a non-native English speaker, I have the tremendous advantage that I can do things that some of you native speakers cannot always get away with. And one of these things is to create acronyms that maybe sound funny to most people, but that we're okay with. So for this topic here of what is cooling the tropopause above tropical cyclones, I was writing a paper, writing a draft, and I kept, in this draft, I kept saying tropopause layer cooling, tropopause layer cooling. And I was sick of writing that, so I just started abbreviating that TLC, tropopause level cooling. Completely unaware of the fact that TLC is already taken, and it sounds kind of funny in that context, but it made it in the final manuscript, and it's under review right now, so I guess we'll see if people think that's funny or if we need to change that. But yeah, so what is cooling the tropopause above tropical cyclones? Well, maybe for this crowd, I should also say why tropical cyclones, because maybe that's not something that is a primary focus, at least for most of you. I hope I didn't lose anyone there. But so what we are really after here is the effect of convection on the TTL on very large scales. And as such, I'm really using TCs, tropical cyclones, as a kind of deep convective event. That's really it. I'm not really interested in the nitty-gritty details of what happens inside a hurricane, at least not for this talk. I'm much more interested in a large-scale response that they produce. And so yeah, sustained, organized deep convective events, which are known, and Bill has done a lot of work on this as well. They produce these kinds of deep convective systems, produce responses on very large scales. The MJO produces responses on scales, 5,000–6,000 kilometers, and TCs produce responses on scales of like 1,000 kilometers. And TCs, they don't produce a large fraction of deep convection globally, but now we're starting to understand that was the objective debate for a long time, but we're starting to understand that TCs also contain a disproportionate fraction of convection that penetrates the stratosphere. And so the reason I said there's debate about this is because we didn't have, until recently, we didn't really have observations that can really tell us that for sure, and so I'll show some results that sort of confirm this idea. And so if TCs contain a disproportionate fraction of deep convection that makes it in the upper TTL and in the stratosphere, then maybe it's reasonable to expect that TCs may also play a disproportionate role in setting the water content of the stratosphere, also the ozone content, maybe more locally, of the stratosphere. So this is your link to chemistry for the ACOM seminar. If you cool the tropopause, then understandably you will dry the tropopause. If that cooling lingers around after the hurricane has passed, then maybe it's possible that you have increased freeze drying for air parcels that travel through the TTL and into the stratosphere. And then it's also possible, I don't know if we really have observations to look at this, but we think that tropical cyclones are able to put air into the stratosphere that is poor in ozone, and so may participate in setting the ozone content there. And lastly, maybe the biggest difference in focusing on deep convective systems like TCs versus any other kind of deep convective system is that TCs move around. They move around a lot. They move poleward. They transport a lot of heat and water vapor with them in the troposphere that they may just deposit in the mid-latitudes. And in the upper levels, well, we don't really know what's going on. At least that's my understanding. And that's one of the reasons why I look at the upper level processes in tropical cyclones. So this is the basic motivation. The other motivation is that a better understanding of what happens at the tropopause above deep convective systems like tropical cyclones can help us inform help us understand the feedbacks between that cooling and then the tropical cyclone below. So this is a busy diagram that shows the typical cloud structure. So you have the eye wall there and some rain bands. So this is the typical cloud structure for sort of the average tropical cyclone. And then you have the in, up, and out secondary circulation. So with an inflow layer near the boundary layer, updraft here mainly in the eye wall, but also in rain bands outside the eye wall, and then an outflow layer which is located roughly near the typical level of outflow for convection, so 12, 14 kilometers, but sometimes can extend up to the tropopause. This is also something I would argue we don't have definite observations of, at least not a whole lot of observations of. So anyway, in this kind of setup, when you have cooling of the tropopause layer, there in blue, the first feedback that you might expect is that will destabilize the upper troposphere to convection and potentially produce stronger updrafts and cloud top heights. And so in turn, intensifying this in, up, and out secondary circulation. And so potentially, and this is an idea that's gaining some momentum right now, advecting high angular momentum air from the environment at low levels up into, near the tropopause in the core of the storm. And when you do that, you can produce what's called most people call that a double warm core feature or upper level warm core near the tropopause. And that's been linked, at least in simulations, that's been linked to very rapid changes in intensity, which is an obvious problem for forecasting. So that's an important thing to better understand. Another feedback from this tropopause layer cooling, TLC, is that it may modulate the outflow. This is also an active area of research. There's actually a lot of debate. I was just in Munich talking to a few people there who were very vocal about, the kind of retired scientists who are still in the office every day, very passionate about their stuff, and who don't mince their words about the theories that are emerging about this idea that the outflow may be modulated by external factors and in turn impact what happens in the inner core of the storm. But so if you cool the tropopause and maybe just below the tropopause, in cases when the outflow layer goes all the way up there, understandably you might modulate what happens in the outflow layer, the stratification of it, the turbulence that occurs in it, and we know that will impact the storm motion, the intensity, and the structure as well. And lastly, and maybe that's kind of it's just a suggestion, I guess it's just a speculation from me. This cold air, I don't know where it goes after the storm has passed, but if it lingers around, it's possible that it may impact the next storm. And I don't know how important that would be. Storms tend to form in clusters. You'll have a few storms form in a row, and then any given oceanic basin will be quiet for a little while, and then you'll have another few storms, and etc. So I don't know if that would play a role in this. So these are the basic motivations. I already talked about TLC, and I didn't even really show what TLC looks like. So let's do that. So some historical observations. This signal TLC was actually described a long time ago. I think there's a paper from like 1936 that shows something like TLC. So here you have a composite from radiosondes from the Frank paper, the composites in the Frank paper. So you have a tropospheric warm core. Here you have 15 degrees temperature anomaly, and above that you have that pancake looking, but really it's more like a sheet of cold air that extends on scales up to about 1,000 kilometers. And then over here, this is not a composite, this is just a skillfully drawn interpolation between individual radiosondes for an individual storm. So you have Here you have the warm core and the troposphere. It's a bit of a mess maybe from where you are, but this is the tropopause in dashed lines, and at the tropopause there's this cold core there that the author had suggested mechanisms for already back then. So back in 2016, which is already a long time ago, I had updated these results using cosmic GPS radio occultation temperature data, because these radio sound stations are not inside of tropical cyclones most of the time. So we don't really, this is a good first picture, but it doesn't really, it's not very helpful if you want to really understand how things work. And so I had updated these results using cosmic. So this is the evolution of the radius, altitude, structure of temperature anomalies within storms globally. And the time axis is relative to maximum intensity. So this panel is during intensification. This is around maximum intensity, and then this is the decay phase where you have extratropical transition occurring or landfall or whatever else. And so you can see, even as the warm core here is developing, you already have that sheet of cold air. In this case, it's just below the tropopause that is forming, and it's already extending to very large radii. And then as you go in time, you can see that that air has a tendency to, so the signal maximizes here around maximum intensity, which is kind of coherent with convective vigor. And then after maximum intensity, the signal has a tendency to move away from the storm center, which is something that we couldn't really see with radio sondes. So this is a temperature anomaly. And I call it TLC, cooling. And so I kind of wanted to show the actual temperature tendencies so that I can show that there's actually cooling, and where that cooling is, because this is the result of some tendencies that occur somewhere, but then we have to, the tendency might tell us something a little bit different. So this is the tendency from cosmic as well. I had to do a little bit of trickery to get to this result, which is just basically choosing a time dimension so I can use these temperature retrievals from cosmic and calculate tendencies from that. So these, I would say, should be taken as, orders of magnitude, not like, don't look at the details too closely, but basically, so radius, altitude, composite again, and it's all in the upper troposphere and lower stratosphere because that's where cosmic is most accurate. And you can, so the googly eyes there, that's the median tropopause height from cosmic as well. And you can see that at and just above that tropopause, you have tendencies of about, a Kelvin per day. And then below that, you have, this is your warm core tendencies there. So this is what we're working with, and these values will be useful later when I try to explain which mechanisms might be producing the cooling. So great, there's cooling, but so why is there cooling? Well, from a sort of non-mechanistic approach, we can just say that there has to be a cooling, that it's an inherent response to warming. And to try to understand that, I would say just give yourself a hydrostatic atmosphere at rest and prescribe a source of heat in the troposphere. When you do that, you're going to create horizontal pressure gradients. And if you put yourself at the top of the atmosphere there, if you say the top of the atmosphere is where pressure vanishes, you have no circulation because there is no air to circulate there. For that to hold true, you need to have zero horizontal pressure gradients at the top of the atmosphere. And for that to occur, you need to have some sort of compensating cooling in the column where you have warming. So, there must be a cooling in the column. Otherwise, you'll have gradients up there, and your constraint doesn't work anymore. But so, how does that cooling form? Well, when you put that source of heat, you create a circulation that looks a little bit like this, that can extend above the source of heating because parcels gain gain inertia, and they're not going to stop just where you have no heating. They're able to travel a little bit further than this. And anywhere where you have this criterion there, where the vertical motion result from that circulation is larger than the ratio of, the amount of heat that you're releasing to the static stability, then you can have adiabatic cooling. So, just above the top of the heating, Q is 0, so you'll have cooling anywhere where omega is positive. And anywhere where Q is very small compared to the static stability, so realistically near the tropopause and above, any amount of ascent will also create cooling. And so this is kind of how we understand, this cooling, how this cooling may form, at least from a very simple, idealized hydrostatic point of view. And here's the associated pressure response. Okay, so one first good clue as to why this may be one of the primary mechanisms for the cooling is that Reanalysis data sets are able to capture the cooling. And so I'll show that here. If reanalyses are able to capture that cooling because they're coarse and sort of smooth behaved and mostly hydrostatic dynamics, well then this is most likely what's going on in the reanalysis. So here's the time evolution. So it's time relative to maximum intensity again, which is it's lifetime maximum intensity, but it's just in the center there. So this is the cosmic observations with the -1 degree anomaly line in black. And then this is from era interim, and this is from MERA 2. So you can see that during the intensification period, which is mostly in the tropics, these reanalyses are able to capture the signal. And then after maximum intensity, they struggle a little bit. The signal lingers around for reasons that I haven't really figured out why yet. But it's important that they're struggling because it's telling me that most likely data assimilation is not what's producing that cooling if the mechanisms that I showed earlier are not acting. Yes, Eric?
So is this over all ocean basins and all strengths of storms and over
Yes.
decade-old?
Yes, this is all basins together just because that way we have good statistics. We're good enough for cosmic, and it is for 1990 through 2014. Yeah.
Do you see any intensity difference in signals like Cat5 versus 1?
Yeah, so yeah, basically the strength of TLC, of the cold core, goes with the strength of the warm core, which, I'll show what mechanisms we're expecting to produce that cooling on top of the broad scale ascent, but it just kind of makes sense, yeah. Yep. And so I was saying that data assimilation is not something we expect really matters to produce this cooling, because, why would it struggle there, not here, if data assimilation is what's producing the signal that we see in real life? And also, in the vicinity of tropical cyclones, the data assimilation scheme most likely tosses out a lot of data because the reanalysis is producing a storm that may be a few hundred kilometers away from the real life, the real world equivalent. And in those cases, the data assimilation doesn't account for that data because there's too much of a gap between the observations and the reanalysis. So we think that this is kind of the main mechanism that happens in the atmosphere, but this is all very smooth dynamics that doesn't account for a lot of stuff that happens in the real world, such as these three mechanisms that they're kind of in popularity order, I guess, or at least from my experience. So the first idea is that there's cold air near the tropopause because of cloud top radiative cooling. That's an idea I've had a lot of people comment about at conferences and workshops. You show these results and people tell you, well, of course it's cold, it's just because it's a cloudy area and clouds reach the tropopause and they cool it because that's what cloud tops do. To us, that didn't seem like such a reasonable expectation because when I started my PhD, I wasn't that familiar with tropical cyclones. I knew more about deep convection in general, and I knew that in the tropics, above, say, 14 kilometers, the amount of convective clouds you get is just very minimal. And so, that there would need to be a significant difference between the deep convection that occurs in a tropical cyclone versus outside a tropical cyclone for cloud top radiative cooling to really matter. But so that's the first mechanism. Another mechanism, which was actually proposed in the late 60s, and that hang out until now, is that this cooling is just from overshooting tops. So individual cloud elements that overshoot their local level of neutral buoyancy and produce localized cooling through adiabatic expansion. And I'll come back to that one, but we also don't really expect that one to matter a whole lot. We have good reasons to. And lastly, and I don't think this is popular at all, actually. I think this is mostly something I'm trying to drag with myself and get people on board with. But I myself don't have, I'll show some of the results I have, but I don't have a whole lot of explanations there. But convectively generated gravity waves, that propagate upward and outward from the storm center may trigger ascent and divergence at the tropopause. At least we know that gravity waves and Kelvin waves on very large scales can produce significant temperature perturbations, especially near the tropopause. And so it's not completely clear how that would work so that you end up leaving any kind of signal behind, at least not to me, but it's still an idea that we're working on. So I'll go through these mechanisms and show you some results, and yeah, please ask questions if you have any. I'm happy to discuss stuff. So for cloud radiative effects, we need good cloud data, obviously. And until relatively recently, we did not have that. We only had radar data from CloudSat. So here, over there, is a typhoon with the CloudSat overpass that went right over the center, which it's not that frequent, but we have a few of these. So this is the radar reflectivity. And from that radar reflectivity data until maybe 2012 or 13 or so, we were using this data along with other data, but to produce a cloud classification product. So a product that tells you what kind of clouds are where, which is very useful for us, and I'll explain how. So for that overpass, this radar reflectivity product tells you that everything that's in yellow, that's a cumulonimbus, so a deep convective cloud. Everything that's in dark blue is a cirrus. There's some altostratus, altocumulus, cumulus. I mean, there's all kinds of clouds. The problem with this data set, and especially for us, for tropopause level research, is that the radar is just not that sensitive to small hydrometeors and optically thin clouds. So it's missing out on a lot of things, thin cirrus layers that do really matter for radiative transfer calculations. And so recently people have used the LiDAR data from Calypso, which flew for a few years the same orbit as CloudSat. And so this is the result there. This is the cloud classification product from the combined radar and LiDAR data. And you can certainly see, so the dashed line there, that's 17 kilometers, so the climatological tropopause or so. And you can see over there, you have all these thin layers of cirrus clouds that are not captured by the radar alone. And then you also have another collateral is that some classifications or some clouds are reclassified. So this one was thought of as a deep convective cloud, and now it's a nimbostratus. That's not very important, but just to kind of show you how this data set has improved. Another improvement is that, and maybe it's hard to see, but the tops of these cumulonimbus there is a little bit higher once we include the LiDAR data, and that's just because the LiDAR is more sensitive to the little fuzzy things that detrain from the cloud top that you can still consider as a part of the cloud top. So as soon as I got my hands on this data set, I just produced a plot that would motivate this research, that would motivate why would we ever think that clouds matter at the tropopause. So this is it. This is a histogram that shows the cloud top heights for deep convective clouds. In blue, non-associated with tropical cyclones or typhoons in this case, and in red when it's in the inner core of typhoons. So you can see a clear difference. The median cloud top height for deep convection that's not associated with typhoons is 15.5, and it jumps to 17 kilometers for deep convective clouds inside typhoons. So, you may say, even though we don't have tropopause height data for each of these cloud elements, we can't for sure say if they're above the tropopause or not. But if the climatological tropopause is at 17, it means that half of the time there's potential for clouds and typhoons to reach above that. And so that's really what got us started with the research, is that there is indeed enhanced potential for cloud radiative effects to matter up there. And I don't think that was very clear, because the last time that was looked at least that I'm aware of, was in 2009, a paper that used brightness temperatures, for proxies, for cloud top heights, and in conjunction with reanalysis data to try to tell when clouds are above the tropopause or not. And that was a great first clue, but it also suffers a lot of limitations from reanalyses and from brightness temperature data uncertainties. So this is really, I think this is kind of an exciting result. The next thing I did was to update the vertical distribution of clouds by cloud type, at least for the cloud types that I care about for when it comes to radiative effects near the tropopause. And so I'm showing the occurrence frequency as a function of radius and altitude here for cirrus clouds. So you can see, so this is 10 kilometers there. So we're mostly looking at the TTL in this plot. And you have, in the TTL, you have between 10 and maybe 40% of the time you have a cirrus cloud. It's not like groundbreaking stuff, but it's nice to have the vertical distribution because in the TC community, we know where things are horizontally from looking at satellite pictures, and the vertical is just much harder because there's not that much profiling satellites out there. For cumulonimbus, so deep convection, you can see the eye wall there with half of the time you have, or at least half of the time you have a cumulonimbus cloud there, which is not very surprising. And in the environment, you have more sparse rain bands or intermittent convection there. And in the little googly eyes, that's the median cloud top heights for deep convection with, I don't know if you can see the little circles there, that's the 90th percentile of cloud top heights for deep convection. So again, kind of showing us where in radius there is potential for clouds to reach the tropopause and matter near the tropopause, radiatively speaking. That's really in the inner core here, like inside the 300-kilometer radius, which corresponds to what a lot of people like to call the main convective region. And finally, this is just to kind of, again, not groundbreaking, nice to have. The white hatched area is where the fraction of all clouds is at least 80% cumulonimbus plus cirrus. So in the TTL, if you want to look at cloud radiative effects in the TTL, the first thing you should do is just start with cirrus and cumulonimbus because they explain most of the cloud fraction there. So I took this data set and I separated it in different cloud scenarios that I think would matter near the tropopause. So mostly made up of deep convection or cirrus clouds, of course. The first case is the case where you have deep convection reaching the tropopause and then nothing else in the column. The other extreme case would be this one there, where you have cirrus alone in the column, nothing else, and cirrus at the tropopause, because that's what I care about right now. And then there's an intermediate case where you have cirrus at the tropopause, and then below that we allow any kind of mixed cloud, different layers, different heights of convective clouds, different, shallow stuff, stratiform clouds, anything really. And so the reason why we do that is because the radiative effects of clouds at the tropopause depend very much on what's underneath, at least for cirrus clouds. So for cumulonimbus clouds, you expect radiative, cloud top radiative cooling. There's just radiative flux divergence for Longwave up there, and so you have radiative cooling. For cirrus clouds, if there's nothing else below, then you might expect Longwave warming, simply because cirrus clouds would be absorbing more energy from the warm surface than they're able to emit because they sit at the coldest temperatures in the lower atmosphere. And then in the case where you have stuff below, when the atmosphere is populated with deep convection, well, in some cases, if it's high and cold enough, it might emit little enough that then the cirrus at the tropopause is able to cool the tropopause radiatively. That's been kind of explored by a paper by Dennis Hartmann and co-authors in 2001. This idea that even sitting at the coldest temperatures, cirrus are able to radiatively cool the TTL, I should say, if clouds underneath are high and cold enough. And high and cold enough in general means at least like 13 kilometers. If you have anything above 13 kilometers, we expect cooling. And then in the other cases where it's more layered things or shallow things, then you would still expect to have long wave warming. So I took the data set and pulled these cases out of the data set. I'll spare you the details and quantify the long wave radiative heating rates associated with them. So focusing here first These are the median in thick lines. So for example, this is the median there. And then in hatched is the interquartile range. So just shows you the statistical spread. For the cloudy sky long wave heating rates, so the clear air sky, the clear air contribution is not included there. So there's no 2 degree cooling, 2 degree per day cooling in the troposphere. None of that. It's actually separated and it's here. So for the case, the black case here, that's the case where you have cumulonimbus reaching the tropopause and nothing else below, or nothing else aloft, I should say. It's actually not reaching just the tropopause, it's reaching that layer in gray there, which is, you know, a near tropopause layer, because we don't have tropopause level data. We don't know where the tropopause is from that data set. And so for this case, you can see you have this, you know, very strong cloud top cooling, and at the tropopause, you still have a little bit of cooling, but by and large, it's just very small temperature tendencies, and especially above the tropopause, there's just nothing there. And if you remember earlier, the temperature tendencies, like the total temperature tendencies I showed, the signal tends to maximize over there. So already it's starting to look hard. It's difficult to justify, like it's difficult to explain TLC, even with the strongest cooling from the deepest clouds. Like even in that case scenario, it's hard to explain. And then for the CI case, the cirrus case, so you have cirrus in that layer and nothing else below. That's the blue case, so you have warming there. It's not directly relevant to explaining TLC, but it's nice to have a quantification of the radiative heating rates there. And I think actually I can just skip the rest. Or maybe just explain. So the mixed cases, the orange and the magenta lines, those are the cases where you have cirrus at the tropopause and then a mix of clouds below. And I split them into cases that cool the tropopause and cases that warm the tropopause. And then I look, and this is the plot here, I look at the cloud type for these cases. So you have, this is a cloud type as a function of altitude, as a function of the cloudy sky, long wave heating rate, average inside of that layer here. So cases that cool the tropopause layer are on the left, and cases that warm it are on the right. And you can see that when you have cooling, so again, you have cirrus in the tropopause layer, and then below you have whatever you want. When the cirrus are cooling the tropopause is because you have yellow stuff, which is cumulonimbus. And then when you warm the tropopause is because you have more mixed low-level and stratiform clouds, which makes sense. But again, it's like a good sanity check for this data set, because there's no equivalent data set that we can compare it with. So these, I think the reviewers for our paper are going to have to trust us on these. You know, there's no other, we don't have anything to compare it with, at least nothing that's based on observations. So it's nice to kind of try to make sense of it. So these cloud cases, which I pulled out, they don't happen, you know, they explain a lot of the clouds in tropical cyclones, but certainly not all clouds. And it also doesn't account for the fact that there's a lot of clear air in tropical cyclones. So now we have to take these cases and sort of weigh them according to their frequency of occurrence and add all the rest up and look at the gross radiative effect of clouds in tropical cyclones. So this is the easiest one to look at. So radius altitude composite of the cloudy sky long wave heating rates. So including clear air, including cloudy stuff that does not fit our three cloud scenarios that I described earlier. And then you have the tropopause and the googly eyes again. And then in the back, that -1 line here, that's the total temperature tendency in Kelvin per day that I showed earlier. That's derived from cosmic. And then that thin line is -0.5 degrees per day. So it's just like a visual help to see how much you can explain, how much TLC you can explain from those radiative heating rates. So in these plots, and so this is the all sky contribution. So it includes this thing plus the clear sky contribution, which is basically a cooling in the troposphere and then a slight warming in the tropopause, near the tropopause. So you can see the signature of the main convective region inside, 300 kilometers. So you have here, you can see in cloud long wave warming, and this is the cloud top, right? And you can see that you have, like we expect, we have cloud top cooling all the way to the tropopause, but then above that, very, very quickly, you just lose any kind of signal. At larger radius, you have in-cloud warming from cirrus clouds or nimbostratus, or stratiform clouds in the upper troposphere. And when you add the clear sky warming there, so you switch from slightly cooling the tropopause, clouds slightly cooling the tropopause by 0.01 Kelvin per day or 0.1 Kelvin per day, and then when you include the clear sky contribution, it's just a warming. So these results tell us that you can have some cooling, like the TLC signal. Some of it can be explained through cloud radiative effects, at least at small radius, there where you have the most active convection, the deepest reaching convection. But at large radius, it's just you can't explain a cooling. You have to have another mechanism to produce cooling there. Which is, it may seem obvious now, looking at it, because it's, well, yeah, this is a convective region and it's just, it's forced convection, it's really extreme. So maybe, you could expect cloud top cooling to matter there, and that, it's not groundbreaking. But to us, we didn't know that, we didn't know how far that would extend. We didn't know how high that cooling would extend. And I also didn't really expect to have such a strong warming at large radius. And so, having such a large impact from radiation onto decreasing TLC, that is formed by whatever other mechanism there is acting. So first mechanism, okay, you can have some cooling, but it's at small radius only, you need something else. And then I should also say that for deep convection outside of tropical cyclones, so where cloud top heights are much smaller, 1.5 kilometers smaller, then this looks even worse. Like you couldn't explain any kind of tropopause level cooling from radiation in those cases. So now we can look at the other mechanism, so the overshooting and the gravity waves. Let's just look at some eye candy because it's nice. If I can make it happen. This is terrible. Okay, so this is in a typhoon, and you can see all these little bubbling things that are overshooting tops. If you've looked at these kinds of images for continental convection, it might seem very underwhelming, which it is, because updrafts are typically much smaller above marine convective systems. You can also see very rapidly expanding. It might be hard to see, but gravity waves traveling outwards, maybe especially towards the end when the sun is low. So this is what overshooting looks like in TCs. Here's another video. So you can see this turret there that just exploded into a large cirrus shield with massive overshooting tops there. But I mean, when you look at the whole area, there's just that one little thing there. The rest is just it's an envol. There's not much happening. Here's a still picture, just because it's really pretty. This is at sunrise for Hurricane Dorian recently. So you have all these overshooting tops there, and then associated envols. So for this mechanism, so first of all, it's hard to observe overshooting tops. It's really hard to do that, especially with passive sensors. The simple reason being that above these overshooting convective tops, you may very well have subvisible or near visible cirrus clouds that create very large uncertainties in brightness, temperature, cloud top height retrievals. So from geostationary imagery, where we can see everything, and we can see everything with very high temporal resolution, we can't really use that to look at deep convective overshooting tops. At least we could, but it's just very uncertain, because see here, so this is from CloudSat, which is an active retrieval method. But so this overshooting top, that's about 1 kilometer height. That's within the uncertainty for cloud top heights retrieved by brightness temperatures. So difficult to observe. When you get lucky like this, the 1 in a million shot where CloudSat goes right over the overshooting top right at the right time, You can do something with it, but by and large, trying to have a global climatology of these things would be very challenging. So that's kind of one of the reasons why we're not going to do that. And the other reason is just because we expect, for these turbulent things, I kind of want to say what goes up must go down. You force something to go up and it cools locally, but because it cools, it creates a heavy pocket of air that then has a tendency to sink. And so there's a really nice paper by Fritsch and Brown in 1982 that simulated a continental system, so where overshooting is more prevalent than over the ocean. And they ran the same simulation, in this case where they allowed cooling by overshooting tops, and in this case where they did not, which it's kind of wizardry to me. I'm not exactly sure how they did that. I think there's some parameterization going on there that they can just turn off or on. But when you allow cooling, so this is the vertical motion, so positive, negative here, subsidence on the sides. When you allow overshooting tops to cool locally, you have a tendency to produce subsidence on mesoscales, and so compensating warming going with that. And so, on the for the life cycle of or a lifetime, I should say, of a hurricane, so a few days or a few weeks, we don't expect overshooting to really leave any kind of signal behind, and mostly just compensate itself, which I think is an important message, because in the tropical cyclone community, at least from comments I've gotten, it seems like that's still a very prevalent view, and it's been proposed very early on, and I think a lot of people are kind of bent over, they really want this to be the explanation for tropopause level cooling. And lastly, for gravity waves, here's some more eye candy. So you can see these arc-shaped cloud structures there. That's just gravity waves propagating outwards. And maybe, can you see them here? Is that you can see these little ripples in that circle? I don't know if you can see them. They're there, trust me. But so on very various scales, you have these gravity waves that are just, propagating outward from the center. And sometimes we can see them in the cloud field, and sometimes we can see them with infrared imagery. So there's a system here that is emitting small scale or short wavelength gravity waves here, which is kind of analog to the ones that I showed on this plot there. But then on very large distances, of 2,000 kilometers or so, you have these huge gravity waves that are also associated with this system. And so I like this idea of gravity waves maybe, being one of the dynamical reasons why there's cooling is, they can explain, they can be seen very far from their source, and we know that they trigger significant temperature variations, especially near the tropopause, which is where our signal tends to maximize, or just above the tropopause. And so now we just need to explain how these gravity waves might interact to leave a cooling behind, because it's a wave, so it has a warming and a cooling and a warming, right? So how do they leave behind a cooling? So that's something that I'm working on. And actually, this is from this morning. I'm looking at simulations of hurricanes in which gravity waves are overwhelming. And here's a 30-member average of the potential temperature departure from the initial state, and as a function of time and altitude. So you can see this is just our tropospheric warm core, which maybe, Rosimar, you might tell us that maybe that's not very realistic. I don't know. These simulations are a little funky, but they do produce a cooling near that black line, which is the tropopause. And they also produce a cooling here, just above the source of warming, which I kind of understand as the first mechanism that I showed earlier, this overshooting. It's not overshooting per se, but this secondary circulation that extends above the source of heat that might produce some cooling there. And then maybe also at the tropopause, or maybe some other mechanisms are triggering cooling there. And one of the reasons why gravity waves are potentially responsible for this is this plot. So this is a radius time plot, same simulation, 30-member average. So this is the warm core at 10 kilometers, so through here, which arguably is maybe not the best level to pick, but to give an idea. And then this is near the tropopause. So you have these cooling pockets, which we've seen here near the tropopause. And again, yeah, actually maybe I should pick a level just above the tropopause, but again, just as an idea. But these pockets of cooling, they kind of move around like gravity waves do, and it's very obvious here at 19 kilometers, which is just two and some kilometers above the tropopause. You have these correlated structures that very, very clearly show some gravity wave structure there, and propagation speeds are consistent with gravity waves as well. So now I just need to get to work and figure out how this is happening.
Louis, tell us about these simulations.
Yeah. So it's a CM1 2D simulation of a hurricane, and the 30 members are just, it's just like stochastic noise in the boundary layer. There's no radiation, there's just a Newtonian cooling term, and it's a fixed SST case on an F-plane, yeah, with very high, so the main difference here, and there's so much stuff to do there, but the main point with these simulations is that they are 150 meter vertical resolution throughout the troposphere, which is probably 3 times finer than the average simulation for these systems. And so one idea is that when you choose a fine enough resolution up there that can capture gravity waves as they explode in magnitude in the stratosphere, when you do that, then you can resolve the gravity waves, and they're not forced to dissipate. If you chose a very coarse resolution, say 0.5 kilometer, then these gravity waves cannot be resolved, and they just numerically dissipate and deposit their momentum in the stratosphere and potentially produce very different feedbacks than when you are able to capture them fully.
How high is your model top?
So the model top is at 35 kilometers, and I run into some serious issues there. So this is the bottom of my sponge layer, and I have a top at 35 kilometers. The reason why I have such a deep sponge layer is because when I pick a resolution this fine, I resolve gravity waves, and they're able to just bounce against the bottom of the sponge layer. And so some of these things there might be partial reflection of gravity waves against the bottom of the sponge layer, which is something I just cannot seem to get rid of. So yeah, it's kind of challenging. I kind of understand why people were running simulations that are not that finely resolved.
The gravity waves generated by the overshooting.
Yeah, everything is included there. Yeah, yeah.
That would play in for
Yeah, so I wonder what amplitude gravity waves you would get for, say, a single overshooting top versus the mountain that the tropical cyclone is. Actually, I think maybe that's from the Fritsch and Brown paper. They describe these gravity wave sources as being just the mountain of the tropical cyclone that just moves through a region of high static stability. So that would be interesting to see. A lot of the time, if you look at one member, you'll see a single deep convective event triggering a bunch of gravity waves, but not necessarily an overshooting top. Because things are not that unstable in this model. Yeah, it's a very moist neutral case. Yeah. So yeah, gravity waves, a lot of work. Overshooting tops, well, it seems like maybe not. And broad ascent and divergence is most likely the main mechanism. And in the special case of tropical cyclones, maybe you should account for radiative cooling at cloud top, especially in the inner portion of the storm and for the lower TTL. So these are the takeaways. I mean, I just kind of read them out loud, but here it is. So if you have questions, we have time. It's been 45 minutes, so.
We've got lots of questions, but any more questions or discussion?
So in the slide where you had cosmic with air interim and Mara, you're seeing cooling, I think it was 4 days. Prior to the main sort of mass attention.
Yeah,
Yeah, that was 6 days.
6 days, yeah.
So, but you're having cooling
Yeah.
But afterwards, then you're like, all of a sudden you're not cooling. So what's happening?
Yeah.
Normally when you don't have a storm, like how far out would you have to go to not see that cooling?
Oh, in time?
Yeah, in 6 days.
I think you can, I mean, so 6 days is kind of the earliest tracks start at 6 days before maximum intensity. Before that is just too difficult to define the system. So we can't go back as far back as we would like to. But I suspect you would have to go back pretty far because so what happens here is that you still have a tremendous amount of latent heat that's being released. It just doesn't necessarily show up as a temperature anomaly because you're not in a closed circulation that can keep things around. Everything is still able to be dissipated through gravity waves.
Right.
So,
Cooling
yeah,
above.
yeah.
How far back, like what's causing that cooling? If that cooling isn't caused by the storm.
Well, I think it is caused by the storm. I think you still have a circulation already established back there, like a vertical circulation established back there, yeah. It's possible that some of this stuff is also cold air being advected from somewhere else, but because we're at the coldest temperatures in the lower atmosphere, I don't see where that would come, I don't have a good idea for where that would come from.
So then the next question is then on a 4-day time period.
Yeah.
So what's causing the dissipation of the cooling?
So that's
Even though you've still got the storm happening, it's just not as deep.
Yeah, so after maybe 1 or 2 days, you typically move poleward of 22 degrees of latitude. So you move into the region where the tropopause starts to sink really quickly, and you also move over very, much colder sea surface temperatures. So you shut down all convection, you stop releasing heat. So the transient response of that cooling goes away, and then any mechanism that acts to dissipate or mix away that cold air can just remove it. That's not something that is very clear to me, and it's difficult to assess it because models can't really help us there. But that's the understanding, is that this is just a leftover signal. There's no active latent heat release anymore, at least not as much as what you have, during the intensification period. Yeah. Yeah.
So what are the gravity waves actually doing with the energy? Are they moving it into the stratosphere or laterally? Or
Yeah, so
sense of what's going on?
yeah, so I think it's still like an active area of research, but generally speaking, I think gravity waves are understood to transport momentum and energy up into the stratosphere and deposit it there if they are able to break. So if you have strong wind shear, then they're able to break and deposit their momentum there. For tropical cyclones specifically, the literature is unfortunately pretty limited there.
But
Yeah.
trying to figure out in the model
Yeah.
where it's all going.
Yeah, so in the model, one difficulty is that you have to play with high resolution so you can capture these waves, and it would be nice to do a 3D simulation so that we don't have these kind of weird ring structures in a 2D model that are not that realistic at large radius. So yeah, there's a counterplay there. Yeah, there's a lot of work to do. Yeah, Chris?
Really, so I'm surprised you didn't talk about the anticyclone and
Yeah.
vorticity and
Yeah.
connected to that, because it would have that, at least qualitatively, that temperature profile. And
Yeah.
you might be able to explain some of the differences between reanalysis and the real observations, but the fact that I don't know that models really do a very good job representing the structure of that, the sensitive for shear and
Yeah.
and I would also argue that it's hard to tell that your gravity waves are a signal of the geostrophic adjustment that's really happening kind of all the time,
Yeah.
so that they're the result of something rather than the cause. And so I
Yeah.
wonder if you look at this thing as a slow response, a balanced response, if you could explain something.
So the sheer response of the cooling, like how quick that is, or?
Cyclone response is a
Yeah.
slow response to everything that
My understanding.
raises the tropopause because of the
Yeah.
cool, just the structure you have to have when you have one of these anticyclonic
Yeah. So my understanding is that, so this anticyclone seems to be a slower response. It takes more time to establish itself than the amount of time it takes for that cooling to exist at the tropopause. I should say, so in these reanalyses, the anticyclone maximizes around 150 to 200 millibars, quite a bit lower than where the cooling occurs. So no doubt there is, you know, a negative temperature anomaly associated with that. It might just be very small. And I wonder if, you know, I'm kind of thinking about the asymmetries in the outflow layer, you know, because in my cartoon I showed, you know, that there's an outflow layer. I put that on a 2D panel, so it almost looks like you would expect a huge sheet of anticyclonically rotating air, but in reality it's just much more of a channel. You know, there's like 1 or 2 channels of outflow. So I wonder if, from that perspective, when you average all that together, you have that negative PV there to make things rotate anticyclonically, but most of the air around the storm is not rotating like that. So that could be another reason why I tend not to see this cold response to be associated with the anticyclone per se. Yeah. I mean, the outflow layer is really down here, right?
It's just that cooling you would expect slightly above the anticyclone. So
Yeah.
it's consistent that way. And you're right, when you get shear, you can get displacements. So the anticyclones displace physically from the rest of the storm. So the averaging would tend to dissipate your signal. It's just
Yeah.
an averaging issue, like you said. It's
Yeah.
also an averaging issue in terms of storm longevity. Some storms last 10 days before they achieve their
Right.
potential. Some 1. So they could kind of be mixed in there. So it's not clear if you're seeing an intensification or it's just a
Yeah. The choice of time dimension is tough there. I should say that, you know, I guess I would say it's like most likely the anticyclone comes with a negative temperature response, and so maybe you know, at the levels where we have that cooling, and at the same time when you look at the, you know, 6 days before maximum intensity, where most likely you don't have any kind of anticyclonic rotation, or, you know, very, very slow, because you also don't have a secondary circulation that's very well established, or a primary circulation for that matter, right? But in this, you know, early on, you already have that strong cooling present there. So that's kind of what makes me tend to think that it's just a very rapid response to the latent heat release of any kind in the troposphere. Yeah.
Okay, these are great food for thought ideas, and I think you've done a really nice job. The data, I like the end part where you have a high resolution model and maybe do a budget study in your model.
Yeah. That's the idea.
Down a little bit. Okay, we're going to quit for today, and thanks, Louis.
Yeah, thank you.